Yeah, so this is 1 over delta nu. Okay, and nu is related to the wavelength how?
It's
1 over the wavelength.
So
C
propagation.
C over.
Right, so let's just assume free space propagation.
Okay.
Okay, so the derivative of this is what over here?
Minus C divided by lambda squared.
Minus C over lambda squared d lambda. Right?
Right.
Okay. So this is about delta nu, right? D nu is delta nu.
Okay.
So we can just take this and put it in over there. And this is we can just rewrite that as delta lambda.
Yeah. Thank you.
There we go.
Wow. Wow.
Yeah.
I like it.
Yeah. So it's not intended to be really hard.
I didn't know that we should take the derivative and that's equal to.
Yeah. Well, I mean, a derivative, it's just looking at a small change, which is what delta nu is. It's a small change.
Okay.
Thank you.
Makes much more sense.
So I get the first one, we're just supposed to work on it for a while and then we can give up on it. But I'm really curious how you get, because I can kind of see what to do, but I get stuck past a certain point. I can't figure it out. So can you give us maybe a tip?
So, well,
Like,
I'll
what-
give you the solutions.
Well, I think, we know the final answer. Like, we know, so when after homework's due, you'll post the solution.
Yeah.
Okay.
Oh, and that reminds me, shoot, I forgot.
I have most
So when I was a student, it always annoyed me when I turned in my homework and it took forever to get it back. How long have I had your homework one?
Over a week. It's been over a week.
So that's my definition of it's been too long.
Uh,
So in those situations, I have a policy, and we'll see whether you agree with this policy or not. My policy is to just give you all full credit.
as long as you want in the future.
Okay, so I need to remember for Thursday to make a copy of the solutions and hand back your homework for number 1. So, okay. So you can always bug me about it. If I don't give it back to you by the next class period, then it's a freebie. So, and for whatever reason, I just have not gotten into the groove this semester in getting the homework back. So that's my fault. Okay. But at any rate, so with homework 2, you'll get the solutions when I get that back, and you'll see how it works out. Okay, any other questions? Isn't it great to be in a graduate class? Yeah. Okay. So let's think about polarization a little bit again. And I just want to recap this to make sure that we're all on the same page and we've all got it down. So what's our definition of polarization?
Like an equation or intuitive definition,
Intuitive.
like how in phase things are with each other, or I guess what their phase looks like.
The relationship between
Okay.
X and Y component of the electric field.
Yeah, so an electromagnetic propagating wave, the polarization of it is the temporal trajectory of the electric field. So if it's propagating towards you, consider a plane perpendicular. What path does the electric field trace out over time? That's how we describe polarization, what polarization is. So if we take a snapshot of that wave, then the polarization state, meaning that temporal trajectory coming through that plane, we can trace it back along the thing and map out the entire electric field evolution along its propagation direction. And then we unfreeze time, and that is just propagating with whatever the propagation velocity is. Just like we saw in that animation a couple of lectures back. Okay, so in looking at the plane orthogonal to the direction of propagation. And thinking about how we represent this polarization state, we said that there are a number of different representations we could take. If we looked at the field, just the field itself, if we specify the magnitude of the x and the y components and the relative phase of the y compared to the x component, then that gives us the entire description of this elliptical polarization state. And from that, we can get the orientation angle, phi, and we can also get the ellipticity. So if this is half the semi-major and half the semi-minor axes, then the ellipticity is the ratio. So we could then write down the ellipse representation. And the ellipse representation is the orientation angle of the semi-major axis and the ellipticity. And the ellipticity we define as plus or minus b over a. And the plus and minus goes back to the sign of delta and therefore the handedness of the direction of rotation. Alternatively, we could specify the polarization state by the orientation angle and the ellipticity angle theta. And we define tangent of theta as the ellipticity, and then that ellipticity angle is between 0 and, or rather between minus pi fourths and pi fourths. Okay, so that's another representation. We also have the complex number representation, where we just specify a complex number chi, meaning that every point in the complex plane represents a unique polarization state, and chi, we say, is the tangent of psi, e to the j delta, and tangent of psi is equal to ay over ax. And because ay and ax here, let's just write this down, ay and ax both have to be greater than or equal to 0, meaning they can't be negative. If they're negative, then we have ambiguity in the phase, so we can't allow that. And so because these are both negative, that means that psi is between 0 and pi halves. Okay, so with this complex number, just looking at this form of it, we could also say, hey, if I specify psi and delta, then I've completely specified chi, therefore I've completely specified the polarization state. Alternatively, I could say, let me take this delta and simply relabel it as capital delta, and that's another representation of polarization state. And of course, these two things mean exactly the same thing. It's just this is the form you tend to use in ellipsometry. So we then have the Poincare sphere we talked about last time. And with the Poincare sphere, we saw that's just mapping the complex plane onto a sphere. And then we can specify the coordinates on a sphere as being the pair of the orientation angle and the ellipticity angle. And so that'll give us the latitude and longitude of each point on the Poincare sphere. And then, last time, we were talking about Jones vectors. And an unnormalized Jones vector is just the two-component vector, ax e to the j delta x, ay e to the j delta y. And we could pull out the x component, so ax e to the j delta x, leaving behind 1, and then ay over ax e to the j delta. Because remember over here, delta is the y component phase minus the x component phase. And if we wanted to normalize the Jones vector, then it has to satisfy the relationship that the complex conjugate dotted into itself has to be equal to 1. Okay, and so for the unnormalized version, we saw that the electric field complex amplitude we can write as simply the Jones vector times e to the minus j kz. Because remember, in all of this, we've assumed that the propagation direction of the plane wave we're considering is in the z direction. So we've assumed plane wave and that propagation direction. Okay. And then we said, gee, if we had a normalized Jones vector, well, actually, let's go back. I think we wrapped up last time by saying, what information is in this thing anyway? Right? Did we do that?
Yeah. We talked about that.
Okay. So if we just think about it from the point of view of information, what's the information that's in this thing?
Relative amplitude.
Absolute amplitude, so call that the magnitude. What symbol do you want to give it?
C.
See, oh yeah.
Carlos.
Carlos.
That's right. Okay, so what else? What other information is there? Phase. So call it what?
Phi.
Phi, okay.
Polarization.
And then what? Polarization?
Yeah.
So a unit vector representing polarization state. Is this in general complex or real?
Normalized Jones vector also.
Yes, it's a normalized, I mean, it's a unit vector as drawn.
It's complex.
Yeah, in general, it's complex. Has to be. Because in general, it's going to have the form of px, py, e to the j delta, where px squared plus py squared is 1. Because remember, this is the relative phase shift of the y to the x. And when we're trying to determine the polarization state, it's all about that relative phase shift and the relative amplitudes of the x and y components. It's always about those two things. Okay, and then what else?
E to the j omega t minus kz.
E to the what?
E to the j omega t minus kz.
Ah, okay.
In this case.
What are we going for here?
Just space.
Z and t.
Well, this is just the complex amplitude vector.
Yeah, so we don't want.
So there's no time
we
dependence.
don't
We don't want omega.
All right.
Right. So what do we have in a complex exponential?
Minus kz.
Minus j k dot r in general.
Okay, okay.
In general. If we're propagating the z, well, since I wrote it this way for the polarization vector, then you're right, this has to be kz, because I only have two components here.
And then it shouldn't be E of Z.
Hmm?
And then
Right, in which case this is E of z. Yes. Okay, so this is for the case of propagating the z direction. What if my propagation direction is not in the z direction? And I want to write down the complex amplitude vector in that case. What do I do?
same, just we put instead of ZR.
Yeah, it's the same thing. It's going to have a magnitude. There will be some phase. There will be a polarization. And the spatial dependence, e to the minus j k dot r. And then this polarization will just be three-dimensional in general. but it must satisfy this relationship because they're orthogonal. Because the electric field vector has to be orthogonal to the direction of propagation. Is that Carlos?
So this might be a dumb question, but does not the phase give us information about the polarization?
Nope. Polarization is all about the relative phase of the y to the x component.
Okay.
The overall phase makes no difference to polarization. The overall phase, all it says is something about where the origin is. Because if we take our coordinate system and shift the origin, all we're doing is shifting that phase.
But it doesn't change the polarization.
Doesn't change the polarization state.
That makes sense.
So the p hat is just a relationship between the x and the y.
Mhm.
Okay.
And what's important in here, you can kind of see it right here, is the relative phase of the y to the x and the relative amplitude of the y to the x. Those are two things that specify polarization state. Yeah, Jason?
And so phase delta can be visualized on the graph as like the distance this way between the x and y components. Like
Okay, so that
I was trying to
that's
visualize delta.
this phase, right?
Yeah, that phase, the relative phase.
Yeah, that's how I think about it.
Okay, cool.
Yeah, is freeze the electric field in time, and in general it's going to be this corkscrew kind of thing. And if you take a cut through some plane and think about what is the polarization, well, you're always just specifying relative amplitude, relative phase. So you'll have an x component, a y component, and that relative phase is just the shift in z of the y component relative to the x component.
Yeah.
Okay. All right. So any questions about this stuff? This is absolutely fundamental. This is just stuff you have to know backwards and forwards. Carlos?
So I'll ask a question, just because it kind of relates to the homework, but the normalized one,
Mm-hmm.
I'm just having a hard time, the bottom one?
This one or this one?
That one, yeah.
Okay.
How that equals to 1.
How this?
Yeah.
Oh, well, by definition, if we write things as magnitude, phase, normalized polarization state, then by definition this has to be true.
So I guess, how do you get from that top one to that bottom?
This one? Oh, so in this case, we could write p hat as 1 over the square root ax squared plus ay squared times ax e to the j delta x, ay e to the j delta y. So we've just normalized it.
Okay.
So, one question I have is we have this,
Alex, that reminds me. You grew up in the same ward as the Brennings in Albuquerque, right?
yes.
Yes, they're friends of ours. Yeah, we had dinner with them Friday night at Milagros, and somehow you came up. So that was great fun. Yeah.
So, okay, we'll have to talk about that later, but,
Yeah.
so going back to the second form of the Jones vector, where we factored out the ax e to the j delta x.
Right.
Is that part that we factored out, this c e to the j phi?
Yeah. So there's the magnitude. And, well, actually, no. The answer is no. It's really, for this guy, well, so here we're assuming a normalized, a unit vector to represent the polarization state, and this is not a unit vector. So what we'd have to do is,
How do you get that top one?
well, it's just algebraic games, right?
Well, wouldn't we just yank all this stuff out and then normalize?
Yeah. Yeah. And
So p is the normalized result of that.
yeah. Yeah, and then, so if I were to normalize this thing, what would I do? Well, this is not normalized, right? So this is all the stuff out in front. So this thing has the magnitude, the phase, and the polarization state in it. So if I want to make this look like that, what I need to do is say, okay, let's take the square root of ax squared plus ay squared. And then let's take 1 over the square root of ax squared plus ay squared. The product of that is just 1, so no big deal. And then I have ax e to the j delta x, ay e to the j delta y. Okay, so this is equal to that, and therefore this has all of that information in it. So now let's just rearrange things. So let's take that, and let's pull this guy out. So ax e to the j delta x, and then let's no, let's not do that. So this thing, okay, let's do this. Let's pull this guy out. So we have square root x squared plus ay squared and e to the j delta x. And then we have 1 over the square root ax squared plus ay squared. And then we have ax ay e to the j delta. And now that's p hat. This is e.
Wait, that becomes, that's delta y, right? So, just because you have the delta x outside.
Well, I pulled it out.
Yeah.
So this is delta y minus delta x.
Okay, okay, okay.
Yeah.
Yeah. Okay.
Yeah, no, I'm glad you mentioned it. So this thing is e to the j t, and this thing is the amplitude. So that's how we go from here to here.
Excuse me, when you are starting, when we bring the square root of ax squared plus ay squared?
Which one?
The first one.
This one?
Yeah.
What about it?
I mean, how you write it down, just started and said this is the magnitude and this is the p hat.
Well, so all I did was I said, let's start with this, and then let's multiply it by 1.
Okay.
And here's our 1.
All right.
Yeah.
I guess I'm just a little confused as to why we are taking the magnitude of ax and ay, or I guess the squared addition squared.
Uh-huh.
That makes sense. As our 1.
Oh, we're not. We're saying we're multiplying this guy by 1, and that 1 we can configure it however we want. We could say it's 5 over 5. We could say it's ax over ax. It doesn't matter,
So why did we choose that then?
because this is the magnitude of that vector.
Oh, okay.
Yeah. And so if we're going to multiply by the magnitude, we better divide by the magnitude. And then if we take this divided by the magnitude, that's just the normalized version of it.
Oh, that's why.
Yeah.
So for this p hat we have right on the left, right here, just on the left of that line that you drew,
This one?
why does that still have the phase information in it then?
Because I didn't pull it out.
Okay,
Yeah.
and then that's a delta.
And
Okay,
that's a
perfect.
delta, yes. Yeah, thanks for catching that. Okay. So are we happy?
Yep.
Okay, so this should become second nature. Because if you've got this, everything else, it's not too bad. But if you are not 100% on this, then when you work on the other stuff, you can kind of tie yourself up into knots and become confused. Okay. So, the last thing I want to point out is we said last time that if we have some optical system composed of different optical elements, whatever those things are, and we have some polarization state that's incident, and we want to know the polarization state that comes out, then we can use a Jones matrix calculus to figure that out, which consists of determining what the Jones matrix is for each of these elements, and then simply multiplying the input Jones vector by the matrix representations of each of those elements in the proper order, and that will give us the output polarization state.
What are we calling that output, Jones vector? Like the J naught?
J out,
J out.
J-O, yeah, Joe. Okay, so what we want to do today is dig into what some of these elements are, what their Jones matrices are, what the properties of these things, or what properties they have, and then kind of useful things you can do with them. And we won't get to all of the useful stuff today, we'll get to that on Thursday. Here we're just kind of setting it all up. Although we will find some useful things for what we talk about today. Okay, so the first thing that we want to talk about is a polarizer. And a polarizer is pretty much the simplest possible element you can use to operate on a polarization state. And if we set it up like this, with this being our z-axis, so that's the direction of propagation of our light, and here's the x-axis and the y-axis, then if we put a linear polarizer that passes light in the x direction, then our linear polarizer would be basically here in the x-hat direction. And the effect of that is whatever our polarization state is here, what comes out is linearly polarized in the x direction. So it doesn't matter what we put in, this polarizer only passes the
X
component that's in the x direction. So we can write then a Jones matrix pretty trivially as just 1, 0, 0, 0. And so if I have some arbitrary polarization state, and I want to know what comes out, so the output polarization state is just going to be this Jones matrix times the input polarization state. And so we can write that as 1, 0, 0, 0. And then the input polarization state, AX, AY, e to the j delta. And then doing the matrix multiplication, we just have AX 0. So that Jones matrix represents what we mean by a linear polarizer in the x direction. Now, alternatively, we could have a linear polarizer in the y direction, and so the Jones matrix for that would just be 0, 0, 0, 1. And therefore, it only passes the electric field component in the y direction. And so we could work that out, but I'll let you do it because it's pretty trivial. And what we're talking about so far is this is an ideal polarizer. Likewise, this is an ideal polarizer. What's a non-ideal polarizer? Well, a non-ideal polarizer, we'd have a Jones matrix of, I don't know, piece of x, 0, 0, piece of y, say. And we put on the condition that px y have to be in the range of 0 to 1. And typically, Py will be much less than Px. So what does that mean? Well, if we propagate light through this non-ideal polarizer, the output Jones vector will be Px 0, 0, Py times Ax, Ay, e to j delta, and that's going to be Px, Ay, plus Py, Ay, e to the j delta. And because Py is much less than Px, this is going to be really small compared to that. So the y component that passes is really small compared to the x component.
So is that a non-ideal polarizer for an X polarizer?
Yes.
Okay.
Mhm.
Because if it was for a Y, it'd be the opposite.
Be the opposite, yeah. So let's call this Px then. So this is the non-ideal version of that. And now if Px is not 1 here, then that just means we have some absorption for the light in the x direction. Yeah, Wes?
So does the e to the j delta term mean anything?
Here?
Out there?
Yeah, I mean, it's just that there's this phase shift delta of the y component compared to the x component.
But aren't we saying that the y component is more or less like destroyed?
Yeah, and actually I wrote this all wrong, didn't I? I should write this as a Jones vector. So this is Px, Ax, Py, Ay, e to the j delta. So in other words, this is just really small.
Right.
So let's say that what went into the polarizer, let's say that this was our AX, and here we had an AY, and then it has a phase delta. And we go through our polarizer, then what comes out, well, let's say that Px is not quite 1, a little less than 1. So what comes out is basically right here in the x direction. And then here, Py is small. So we just get a little bit right here. And then this is still out of phase by delta relative to that. That's all.
So it'd be like a super skinny ellipse.
Yes,
in reality.
exactly. Exactly. Yeah, and we don't know that it's a skinny ellipse with a semi-major axis here. It could be a skinny ellipse, about that axis. It all depends on what delta is. If delta is pi halves or negative pi halves, then yeah, it'll be about this axis. But if it isn't, then there's going to be some rotation angle. But it'll be really small. Okay, so all polarizers are non-ideal. And so this is why you always specify what the extinction ratio of the polarizer is. Extinction ratio. So what is the amount of pass polarization to reject polarization that makes it through? And, maybe it's 1,000. Well, that's a pretty good polarizer. Maybe it's 10. Yeah, that's a pretty crummy polarizer. Maybe it's 10 to the 6. That's a fantastic polarizer. It's really hard to get there. Okay. And then, of course, as to whether it matters or not, just depends on your particular application. All right, so now let's look at the following situation. Let's say that we have orthogonal polarizers, meaning that here on our z-axis, let's first have a polarizer in x, so linear polarizer in x, and then let's have a linear polarizer in y hat. So the system matrix of this whole thing is just going to be first px, because that's what light will see first, and then py, that's what we'll see second. And let's assume these are ideal. And so this is going to be 0, 0, 0, 1, 1, 0, 0, 0, which is 0, 0, 0, 0. So orthogonal polarization polarizers are not so great in the sense that they just kill all the light. But it turns out that's really useful. In fact, liquid crystals, it all comes back to this. Liquid crystal displays.
That's a turn on and off, right?
Yeah, you have something in between here that changes the polarization state. So you get only linear X coming through, and then you have the liquid crystal in here, and if the liquid crystal doesn't do anything with the polarization state, then this exit polarizer kills it. So the pixel's dark. But if you can rotate the polarization state here so that it comes out in this direction, then it passes right through, and now the pixel's bright. And that's how a liquid crystal works.
Yeah, so I understand this math and kind of conceptual how this works, but like from like an energy perspective, where does that light go? Is it just absorbed as heat, or is it?
So it depends on the nature of the linear polarizer.
Okay.
But there's one of two things happens. Either the polarizer is made from a material that is absorbing in one polarization state but not in the other,
Okay, okay.
which is a dichroic material, in
Okay.
which case then, yeah, the absorbed energy is heat.
Okay.
Or it's made with one or more surfaces that are designed so that you get reflection
Okay.
of one polarization state but not the other.
Okay.
So either or.
Okay, cool.
And in terms of the a dichroic material, as I've mentioned before, if you've got polarizing sunglasses, that's a dichroic material. And how does that work? Well, it's basically just a polymer. And for a polymer, if it's a linear chain polymer, then you just have these, linear chains of carbon atoms with whatever side groups hanging off of them, and they're just kind of like spaghetti all together. And then that's your plastic. And if you take certain polymer chains like this, heat them up, and stretch the material, then what ends up happening is you get these polymer chains that are kind of lined up as you stretch it. And if you've got the right plastic material, then what can happen is that light that is going through it like this, where the electric field is oscillating this way, that can actually take electrons on this backbone and run them up and down the backbone and couple energy from the electric field into the electrons, and then that energy gets dissipated as heat. So in that direction, for polarization in that direction, it gets absorbed. But in this direction, you can't cause electrons to jump from backbone to backbone. So there's no absorption mechanism. So this polarization state just goes right on through. And so that's how your sunglasses polarizers work. Because that's a very cheap way to make a polarizer. It's just with the right plastic. Okay, so now what we want to do is get a little bit better idea of what you can do with polarizers and some of the important aspects of that. So to sort of work this out, it would be helpful to look at the irradiance. And if we have a plane wave that has a particular electric field, what is the irradiance that we calculated using what popped out of all that analysis we did a few lectures ago?
It's the magnitude of E squared.
Over 2 times the impedance of the material. Okay, now what E is that?
That's just the total E, right?
Total E. Total E meaning
Meaning EX squared plus.
meaning the full complex representation of the field.
With the magnitude of that.
So this E is that E?
No, it's just E naught.
E naught, that's it, just E naught, since it's the magnitude
It's just a
squared.
complex.
Okay, so we have the complex amplitude, which is E naught, E to the minus J KZ. I mean, we could say, dot R here, and just make it a general, just going in some general direction. Okay, or is it E naught? Or does it matter?
I think it matters because once you take the absolute value, it just becomes a unit.
Yeah, in practice, it doesn't matter. Because when you take the absolute magnitude of any of these things, it always gives you the same thing, namely magnitude squared of that. So in terms of deriving it though, this is what it was. Okay. Now, for an unnormalized Jones vector, we basically said, let's just give this a different name. Right? Right? Kind of what we went through for the beginning of class. And what information does this have if it's an unnormalized Jones vector? Amplitude, i.e. the Carlos number, phase, and the polarization state. That's what's in there. Okay. So if I have some system then, whatever goes on inside this system, if I have an input polarization state, let me just subscript it with I for the Jones vector, and I've got an output polarization state, and I superscripted that with an O, but whatever. Since I want to get used to the fact that the symbols themselves don't matter, it's just what they mean that matters. Now I'm going to subscript it with an O instead of a superscript with an O. Who cares? So I would have then that the instant irradiance is basically Ji magnitude squared over 2 times eta. And I can write that as Jx squared plus Jy squared, if I wanted to, over 2 times eta. And what's Jx and Jy? So if I write a Jones vector, how do I write it? So AX, AY, E to the J. Okay. Or I could just say, JX, JY. Which case, I really need to do magnitude squared there. Whatever. So I'm playing games with the notation deliberately. Rather than just keeping it all the same every time so you get used to it, I'm deliberately switching it up on you so you have to think about it and what these things mean. Okay, so, but I'll be kind and not do that here. So this would be AX squared plus AY squared, and let's subscript it with, say, an I, indicating the instant light. And then for the output, it's same thing, right? Just subscripted with an O. So AXO squared plus AYO squared over 2 times eta. Okay, so calculating an irradiance given the Jones vector is no big deal. And notice I could define the transmission of this system as the output irradiance divided by the input irradiance. In which case, that's just going to be AX0 squared plus AY0 squared over AXI squared plus AY squared. So that'll tell me what fraction of the instant irradiance actually makes it through the system. That's what T is, the transmission. Fraction of the instant power that makes it through, fraction of the instant radiance that makes it through. Okay, so why are we defining that? Well, because we want to use it. So, let's say that we have the following situation. Let's say that we've got a polarizer that we rotate by some angle beta with respect to the x-axis. So this is our linear polarizer, and it's nominally in the x hat direction, but then we rotated it by beta. So how do we deal with that? Well, we need to come up with the matrix that represents this rotated polarizer. And so we can write the matrix for that polarizer in the x prime coordinate system. If I let this be x prime in the direction of that linear polarizer, then in the x prime coordinate system, I know what the Jones matrix is. It's just 1, 0, 0, 0. Simple enough. But I need to know what the Jones matrix of this thing is in the xy coordinate system. And so, yeah, so if I write the Jones matrix rotated by an angle beta, then that would be a rotation matrix by an angle beta to rotate us from the xy frame into the x prime y prime frame. And then when I'm in the x prime y prime frame, this is the correct representation of the Jones matrix. And now I need to get out of the x prime y prime frame back into the xy frame. So that would be a rotation of minus beta. So if I were to do these rotations in the proper order, then I would get the Jones matrix of the rotated polarizer. So that means we need rotation matrices. So the rotation matrix for rotating the coordinate system from xy to x prime and y prime is something you've had to deal with before, right? Somewhere in some class, sometime.
Sine and cosine.
Yeah, I mean, it's just a simple kind of sine and cosine relationship. So this would be cosine of beta, sine beta, minus sine of beta, cosine of beta, and you can go off and derive it if you like. But that's what it ends up being. And the rotation matrix for minus beta then is just substituted in minus beta everywhere here. And so we have cosine of beta minus sine of beta, sine of beta, cosine of beta. Okay, so we're going to deal with rotated devices a lot, which means we're going to have to use these rotation matrices a lot, which means we're going to get sick and tired of writing cosine and sine of beta. At least I do. Therefore, I use my own shorthand. And because I don't want to write cosine and sine many times, you're going to learn my shorthand. So my shorthand is, this is CS minus SC. Okay, just to make it easy. And then this would be C minus S, SC. So every time I write a C and every time I write an S, now you know what I mean. Okay, so with that shorthand, let's write this down. So this matrix is C minus S, SC. This matrix is 1, 0, 0, 0. This matrix is CS minus SC. Okay, so we need to do the matrix multiply. So if I do those two first, then that gives me CS00. Right? I did the matrix multiplication correct? Okay. So, over here then, I can do this matrix multiply. That gives me a C squared. This gives me a CS. This gives me a SC, which is the same as CS. This gives me an S squared. So if I now expand it out, what I have is cosine squared of beta, cosine beta, sine beta, cosine beta, sine beta, and sine squared beta. And so that is the Jones matrix for a linear polarizer rotated by an angle beta with respect to the x-axis. Okay, so not too bad, right?
Excuse me.
Yeah.
Just at the first problem, the polarizer is in the direction of X or it's not?
So the unrotated polarizer would be in the direction of x, and then we rotate it by beta. And so that's kind of what this is supposed to mean. You start off in the x direction, rotate it by beta.
Alright.
Okay. So let's do a little exercise with this and use it. And then let's understand what it is we do, just intuitively what it means. Because in the end, we don't want to just do mathematical manipulations, we want to understand what it means. Okay, so let's, for our example, let's begin with linearly polarized light in the x direction, and then let's have it be incident on a linear polarizer rotated by an angle beta. And what we want to know is what's the output of that. So let's just draw it. So we have z, x, y. So our instant state here is just in the x hat direction. So that's ji. And then here we have a rotated polarizer. And then what we want to know is what's the output polarization state. And so we can easily write down how to calculate it. The output polarization state is just going to be the Jones matrix for this rotated polarizer, which we called P beta. And then we have the matrix for the instant polarization state, which at one point we called, LX. Actually, I think we call it LX hat. And so if we substitute in, then we have C squared, CS, CS, S squared, and then we have 1, 0 for our linear polarization state. And so that gives us C squared and CS. And then notice the C's common to both. We can pull it out. So we pull out a C, that's a cosine of beta. And that leaves us with a cosine of beta, sine of beta. And that is our output state. Yeah.
So LX is the input.
Yeah.
Jones
Yeah. So this is LX.
And so we're saying that LX has light traveling in the x direction.
Yes, it's traveling in the z direction,
But yeah.
linearly polarized in x. Yeah. Okay, so that was really simple to calculate the output polarization state. Not a big deal. And then the question is, well, what the heck does that mean? So let's think about it. Let's see what it means. So let's draw our XY plane in which we're going to understand polarization state. And to begin with, actually, let me switch this up just a little bit. Here I used a normalized linear polarization state. What if, okay, we'll just start off with normalized. No, let's not, because it's kind of nice to see how it works out. Okay, so if it's not normalized, then we could just write it as AX0, right? And then there's just an AX out here, and there's an AX out here, right? Okay, so our starting polarization is just, we go out here some distance, AX, right? And that's the electric field component we start with. And then we have a polarizer oriented along the X prime direction. And so intuitively, what does a polarizer do? It only passes through the component of the electric field that's in the direction of the polarization pass axis. Now what's the polarization pass axis here? X prime. So we want to know what component of this does the polarizer pass. How do we figure it out? True. So if we take a perpendicular from here, then this has to be the amount that's passed by the polarizer, right? And how much is that? If this is beta. Yeah, so this is just AX cosine of theta, right? That's basically, if we go back to this picture, that's basically the polarization in the X prime, Y prime frame just past the polarizer, right? But now we need to get into the XY frame. So this, what fraction of it is in the X direction?
Cosine of that.
Yeah, so we drop a perpendicular down here, and this much of this thing is in the X direction, and that's going to be AX cosine squared beta, right? And then the fraction of it that's in the Y direction is just here, and that is AX cosine of beta sine of beta. Right? Make sense?
Yeah.
Well, hey, that's exactly what this is. Yeah.
Is that, can you explain why you did that first perpendicular in that manner along X line?
This one here?
Yeah.
So we have, this is the electric field vector we start with.
Yep.
And only the component in that direction will pass the polarizer. Because that's what a polarizer does. It only passes the component of the field in the direction of its pass axis.
Okay.
So it's kind of tricky because it seems like it creates a Y component that was never there.
Well, all we're doing is we're taking this thing and we're saying, hey, choose any rotated coordinate system and break this up into the X prime and Y prime components in that coordinate system. That's all we're doing, which is just a coordinate rotation. That's it. And so we're saying, well, let's take this electric field, rotate it to the x prime, y prime frame, and we're only going to pass the x prime component, so I didn't even bother drawing the y prime component. So that's what we did.
I seem to remember something where if you shine a light through 4 polarizers, each at 45 degrees, you can still get light directly through.
We're going to do exactly that next.
Okay.
Yes.
That's what
Yep, good. Okay. Yeah, Kevin?
So just to clarify, I guess the equations in black, those are the, what's left, right? On
Yeah,
the
that's
normal.
that's what's left in the x, as described in the xy frame.
Okay,
I mean, it's the same thing as this described in the x prime, y prime frame.
that's after it comes out of the polarizer, right?
Yeah. Mhm.
Okay.
Exactly. Yep, you got it. Okay. All right, so sounds like we got it. All right, now, last point here with this example, then we'll move on to another one, is let's calculate the transmission of the system, which is the output irradiance divided by the input irradiance. And the input irradiance is what?
J squared over 2AS. I think it's just J squared.
So a squared over 2 eta.
J, sorry.
Because what's our input like?
Oh,
Yeah. Right. Okay. And then our output irradiance, what is it? Well, we already know there's going to be a 1 over 2 times eta. Those are going to cancel, so forget those. So what's the rest of it?
It has both components, it makes some voltage.
Yeah, so I mean, we go back to this. It's going to be ax squared. And then we have a cosine squared that we square. And then we have, because that's this part right here, right? And then we have this part. So that's going to be ax cosine squared beta sine squared beta. All right?
Shouldn't that be cosine power to the power 4?
Here?
Yeah.
Yeah, it is. I didn't write it very clearly. Cosine to the 4th.
There's that, and x squared.
It's a square.
Oh, yes it is. Thank you. Perfect.
So AX cancels out.
Yeah, ax squareds cancel out, so let's get rid of those. So we're left with cosine to the 4th beta plus cosine squared sine squared beta. And we've got a common cosine squared beta between those two terms. And so we'll pull out that common cosine squared beta. And hey, this is just 1, so what we're left with is cosine squared beta. So the transmission through a polarizer, where the instant linear state is an angle beta relative to the polarizer pass axis, the power that's transmitted, the fraction of the power transmitted, is just cosine beta. Or, sorry, cosine squared beta. This is called Malice's law.
What?
Malice's law. So why is it called Malice's law?
It's not.
Because way back when, before this was understood, some guy was playing around and he found, oh, this relationship, it's always cosine beta. And got his name slapped on it, and there he was. Okay. All right, so, let me just write one other thing. So the more typical form is to write this, that the output irradiance is the input irradiance times cosine squared of that angle. So that's yeah.
And now, can this be generalized where beta is basically just the angle difference between whatever the polarization of the light and the polarizer?
That's exactly right. Yeah. Okay. All right, now let's do the example that Alex alluded to, which is a fun one. let's say that we have a series of 3 polarizers. Let's say the first polarizer is in the x direction. And let's say the second polarizer is rotated at 45 degrees relative to the x direction. And then the last polarizer is in the y direction. Okay? And so let's write the system matrix. And that's going to be a polarizer in the x direction, a polarizer at 45 degrees, and a polarizer in the y direction. So polarizer in the x direction, that's 1, 0, 0, 0. Polarizer at 45 degrees, well, cosine of 45 degrees is 1 over root 2. Sine of 45 degrees is 1 over root 2. So let's pull the root 2 out, and that gives us a 1, 1, minus 1, 1 when we do that. And then, oh, no, that does not give us that. It's a y. Yes, thank you. Okay, we got it. All right, and then here in the y direction, 0, 0, 0, 1. Okay, so that's our system matrix. And actually, you know what? Sorry. Let's just do it all the way out. So, yeah, let's just do it all the way out. So this would be y rotation matrix minus 45 degrees, px rotation matrix of 45 degrees, and then px. Okay, so this basically is that matrix. Okay, so let's just do it all systematically. Okay, so this would be 1, 0, 0, 0. Rotation of 45 degrees, pull out the 1 over square root of 2, and then that gives us a 1, 1, minus 1, 1. This polarizer is 1, 0, 0, 0. This rotation matrix, pull out the 1 over root 2, and we have 1, minus 1, 1, 1. And then this polarizer is a 0, 0, 0, 1. Okay, let's just do it that way. Okay, so we do some matrix multiplies. So this one right here gives us 1, 0, minus 1, 0. And this one gives us a 1, 0, 1, 0. And then if we multiply these together, that gives us a 1, 0, 1, 0. And then if we multiply by this guy, we have the 1 over root 2, the 1 over root 2, that becomes a 1/2. And then we have this, gives us a 0, 0, 1, 0. Okay, so assuming we've done all the matrix multiplies correctly, we get this, and notice it is not that. So some light goes through. Wow, that's curious.
If you didn't have the 45-degree one, then it wouldn't, right?
That is absolutely correct. Without that 45-degree polarizer, no light would go through.
Is that 1 over root 2 or is that 1/2?
1/2, because I've
Two
got
1
two of
over
those.
Ah.
Yeah. Yeah, so, so if we had let's say that over here we have J instant, and we want to know what's J output. So let's say that J instant was X polarized light. Okay, so J output is going to be 1/2, 0, 0, 1, 0, 1, 0. And I do the matrix multiply, and it gives me 0, 1, and look at that. We have Y polarized light that comes out, beautiful. Its amplitude is 1/2 of what we sent in. Therefore, the transmission is what?
However, oh, 2, wait, 1/2 of this.
1/4.
Squared.
Yeah.
Oh,
Square.
Square, yeah.
Yeah. So, by putting this polarizer in, actually 1/4 of the instant light makes it through. Curious. But it's actually kind of easy to understand if we go back to that picture. So we start off with this, let's just call that 1. And then here's our 45-degree rotated polarizer. So this much of that makes it through. It's 1/√2 of this length. And then this guy right here, 1/√2 of that makes it through. And if we have half the original field, that means we have 1/4 of the original power, or radius. So that's how it works. Kind of wild. Okay, so this suggests a very curious possibility, and that is that if I have a whole series of polarizers where, let's say, the first polarizer is an angle beta, the second polarizer is an angle 2 beta, the third polarizer is angle 3 beta, until the final polarizer is at 90 degrees. And I do this with n polarizers. So beta is equal to 90 degrees divided by n. Then, as n goes to infinity, transmission goes to unity. Which is wild.
You're like creating like artificially rotating light then?
Yeah. And it turns out in a liquid crystal, it's not actually a polarizer, it's something else called a wave plate, which we're going to do next. But the same effect happens. It's like the polarization state rotates with the polarizer. And what we're going to see in a wave plate, we can get the same effect, which is why liquid crystal displays work. Which is kind of fun. Okay, so I think we're out of time. So we'll call it there, and next time we'll do wave plates. Any last questions? Oh, and by the way, that's a homework problem. I forget which homework it's on. If you don't recognize it, that means it's on the next one. Okay?